Hello everyone, I am Car-naught and I want to talk about hydrogen vehicle range. While online, I noticed that people were having issues with their Toyota Mirais. Specifically, they just were not getting the range that the company promised. And these were not small differences, with ranges dropping as low as 280 miles under certain conditions, as opposed to the 357 that the EPA suggests. Note, there's also a version of the Mirai with a 402-mile range, but given the 357-mile version is the lowest level, that's what I'll be focusing on today. The real interesting part about this is that not only are people getting numbers different than what the manufacturer stated, they're also getting wildly different ranges. Motor Trend, for example, saw a max number of 358 miles. Donut Media reported numbers as low as 280. Mirai Club tends to be somewhere in the middle. Now, this could be an issue with the Mirai itself. That is a completely valid possibility. However, I recently came upon some data that suggests another answer. Stick around if you want the answer and for some suggestions on how to maximize your range via filling. However, before that, I'd like to ask you to do a bit of science. Before proceeding through the rest of the video, if you own a hydrogen fuel cell vehicle, please state how you normally fill up your car, what time of day, how low you let the tank get, half, quarter on E, what time do you normally fill it up, noon or late at night, what kind of distances do you normally drive with your car, do you normally do frequent short trips of less than 10 miles or lots of longer trips? And last but not least, what kind of range have you experienced with your car? Please answer below before proceeding to make sure your answer isn't influenced by the rest of the video. I'll leave a brief pause before going on to give you a chance to answer. All set? Let's continue. While looking into something else, a common way I find answers to questions no one was asking, I came upon this, what I think might be the answer to why the Toyota Mirai never seems to get its promised range. It's for standard J2601, and what it shows is the maximum amount of pressure that an FCEV tank can be filled to based on its initial conditions. The column of the graph represents the initial pressure of the tank in megapascals. The lower the pressure in the tank, the emptier it is. The rows represent the ambient temperature of the outside air in Celsius. At this point, I would briefly like to thank the SAE for not using freedom units, as I find them very difficult to work with, and this way I didn't have to convert anything. So, what does this have to do with varying ranges? As you can see from looking at the table, the initial conditions present when a driver fills up can affect their max pressure quite a bit, with the max pressure of a nearly empty tank being filled on a warm day being very different from one where the tank is basically full and it's being filled under freezing conditions. Lower pressure in a tank means less gas in a tank of a similar size as opposed to one with a higher pressure. And less gas means a lower overall range. So how much of a difference could this make? To determine the possible differences, we'll be using the ideal gas equation, PV equals MRT. P means pressure, V means volume, M is mass in kilograms, R is a constant determined by the gas being analyzed, in this case hydrogen, and T is the temperature in Kelvin. To find out the differences between mass amounts in different tanks, we'll solve the equation for mass. Then find the mass in each tank under different conditions, and subtract the differences in mass, then times that amount by the MPK, miles per kilogram, of the car to find out how much the range has changed based on the initial conditions of filling. But first, let's get that ideal equation into the form we want, which simply means dividing both sides by RT, giving us P times V divided by R times T equals mass in the tank. In this case, R, according to my old thermo textbook, will have a value of 4.124. Through some trial and error, I was able to determine that the ending temperature is assumed to be 85 degrees Celsius. For volume, we are going to use the Toyota Mirai's tanks because that has the most data associated with it. According to Wikipedia, the Mirai has a volume capacity of 121 liters. Converting liters to cubic meters simply means dividing by 1,000, meaning our V is now equal to 0.121 meters cubed. That gives us everything to start crunching some numbers. Let's start with a very realistic scenario. filling up an empty tank in the middle of the day versus filling it up late at night. Note, an empty tank in this case would be having 2 megapascals left in the tank, which in our equation would mean 10 miles of range left. What's actually left, not what's indicated. The peak temperature in the middle of the day would be 95 degrees Fahrenheit, 35 degrees Celsius, or 308 Kelvin. For late at night, the low temperature is assumed to be 65 degrees Fahrenheit, 18.3 Celsius, or 291.5 Kelvin. So what's the difference in pressure? Well, let's look at the table. For the midday fill, according to the table, the maximum pressure would be 74.1 megapascals. Plugging this into the equation from earlier, we get a mass of 6.07 kilograms, not far off Toyota's 5.5 kilograms claim. As for the tank that was filled at midnight, according to the table, it has a max pressure of 72.8 megapascals. Plugging that into our equation reveals a fill obtained of 5.96 kilograms. Some basic subtraction reveals that there is a 0.1 kilogram difference in hydrogen between the two tanks. Using the MPG rating of the Mirai, we can determine that the person who filled up at noon got 6 more miles out of their tank than the night owl, which doesn't seem like a big deal. But let's take this a bit further. Looking at the table, we can see some of the biggest differences in pressure are from filling a partial tank versus filling an empty tank. So to really see the difference, let's assume the person filling the tank at midnight had a roughly half-full tank, starting at 40 megapascals. According to the table, their max fill pressure would leave them at 69.3 megapascals, meaning the mass they would get out of that fill is roughly 5.67 kilograms. That would leave them missing about 0.4 of a kilogram of hydrogen. That means that they would have a maximum range for a half-full top-off of around 25 miles less as opposed to refilling in the middle of the day on a nearly empty tank. Combine this with a supposed 40 miles of reserve range indicated claimed by some enthusiasts, and that would explain a good chunk of the missing mileage, especially when considering people's filling habits of waiting till they're on E versus filling up at half tank. This is not a realistic comparison, but let's take this to the most extreme possibility. The highest point of filling up according to the chart would be a basically empty tank with an ambient temperature of 35 degrees C or 95 degrees Fahrenheit, allowing the user to get a very nice 74.5 megapascals into their tank. On the other end of the spectrum, we have someone trying to fill up an already mostly full tank when it's minus 40 degrees C outside, which also happens to be minus 40 degrees Fahrenheit, and only able to obtain a maximum pressure of 56.4 megapascals. As an aside, given how dangerous minus 40 degree weather is, please don't risk losing a finger to frostbite for an inconsequential amount of range in your hydrogen vehicle. The person who filled up in the first scenario would be able to get 6.1 kilograms. A very nice tank indeed if they are willing to sweat it out in the hot weather. On the other hand, the person who risked frostbite for a refill would only be able to fill their tank slightly more and get a total fill amount of 4.6 kilograms, or only being able to fill to about 3/4 of a tank. What's the difference in range between these two fills? The fill up during the hot weather got a predicted 381 miles of range, which is nice, while the person who doesn't value their fingers got a 289-mile range, meaning a difference of 93 miles of range. To use other metrics, that's around 2 days of commuting for the average driver, nearly a trip from Fresno, California to Bakersfield, California, or the range of the first-gen Toyota RAV4 EV, according to Wikipedia. I did look into another possible thing causing the difference in range. However, this turned out to be a bit of a red herring, but I do feel I need to put it in order to be intellectually honest. Fuel cells are notably less efficient cold than they are warmed up, possibly as much as half as efficient. The EPA range test that would have been used to determine the range of the car would have been done in one go, starting and running city highway cycles until the car runs out of fuel, meaning that the cell only has to warm up once and then operate at peak efficiency. However, most people do not drive 350 miles every day in one go, and therefore the cells would be operating off efficiency more often, reducing range. However, after some research and calculations, this turned out to be unlikely as a real factor in the range change. It looks like the average driver would only lose about 5 miles per full tank with an average commute and some extreme guesses as far as conditions. Not a significant number, but worth mentioning. Maybe this becomes a factor if the car regularly does sub 5 mile trips and then sits long enough to cool down, but that's not a situation applicable to most people, so it wouldn't be fair to say it's really a factor here. So, what did we learn? The conditions within which a hydrogen car is filled can significantly affect the total range of the car. Filling at half range on a cold night will result in significantly fewer available miles than waiting until the tank is almost empty and filling up when it's hot. Ideally, a driver should fill up when it's 95 degrees outside and when the car is completely empty to get the most range. But does that reflect your personal experience? Let me know in the comments. FCEVs are still unknown, so I would be interested to know if that's not the case. Like this video and pass it along to anyone who you think might be interested in this information. Thanks for watching. Bye.